Hi, in this video we're going to take a look at resistors in series, which is what happens when they're in a single loop, one after the other, and resistors that have been put together in parallel, where the current is allowed to branch through each one separately. And we'll look at each circuit and how to calculate the total resistance. You've probably come across an equation in your physics textbook that says that when resistors are in series, the total resistance is simply the sum of the two individual resistances. So if we imagine a circuit consisting of two resistors, R1 and R2, then that can be converted to a total resistance which is equivalent to the combination of R1 and R2. So we call the total resistance RT, this equivalent resistance, and we say it's equal to R1 plus R2. Now many circuits like this will give you actual values and you will have to make a calculation. For example, if it was 6 ohms and 10 ohms, then it would be, R total would be 6 plus 10, which gives you 16 ohms. Some books may ask you about the amounts of voltage on each one, and they will always be in proportion to the sizes of these resistances, because this V1 will equal the total current times R1, and this V2 will equal the same total current times R2. So it will split up this voltage in proportion to these two resistances. So if there was, say, 12 volts here to be spread out and these were equal, then you would get 6 volts here and 6 volts here. And that follows the rule that the total voltage in the circuit here equals the sum of the voltages across any components on their way round the loop. So we have to drop, say, 12 volts here, we drop 6 of it here, and another 6 of it here, and we end up back at 0. This total current here can be found by first finding this total resistance by adding the two resistors, and then doing Ohm's law with the total voltage and the total resistance being used to calculate I total. So I total will equal V over R, where R is this total resistance. So again, if you had two resistors, say 10 ohms, and another 10 ohms, then the total resistance would be 20 ohms. So voltage divided by 20 ohms would give you your total current. And then you've got the option of coming back to these individual cases and finding what you get when you multiply that total current by that resistance to get a voltage, because you can use Ohm's law on a little bit of a circuit as well. So we could find V1 by multiplying I by R1, and we could find V2 by multiplying this I by R2. So by knowing the total resistance and the voltage being used, we can get a total current. And then we can take that total current back into the original circuit and find a voltage by multiplying current by resistance, and find another voltage by multiplying current by that resistance. So there's a lot you can do with a series circuit, and it'll become more obvious when we get values into these and look at them later. When we deal with resistors in parallel, we have a similar situation going on. We are still trying to turn a circuit with two resistances into an equivalent circuit with a combined equivalent resistance that we call RT. Now we have a different equation for this because it behaves differently. In the series resistances we had voltage dividing up evenly through according to which resistance it was passing through. Here we have a current which is being divided up according to resistance, with the higher resistance if this one was at receiving a smaller current, and a lower resistance if this one was at receiving a higher current. Obviously if these resistors are the same size, then current will split in these branches evenly. So if you had like 2 amps coming down this main branch, even resistances would give us 1 amp here and 1 amp there. So we have this slightly more complicated equation for finding the total resistance of a parallel circuit, and it's that 1 over R total is the same as 1 over R1 plus 1 over R2. So this kind of a problem usually involves you finding some common denominator on the right hand side here, adding the two resistances, remembering then that that is a value for 1 over RT, and when you get your final value, flipping it, inverting it to get a value for RT. And this will become more obvious when we have individual numerical values. Because these are parallel circuits, the voltage here will be across both this resistance and this resistance. So it is possible to work out I1 if you know the total voltage and the resistance here, because I1 will be V total over R1 and I2 will be V total over R2. So it's possible to work out these values straight away if you know these two resistances and this voltage. And then the I total here will actually be the sum of these two currents in the branches, because this current has to split up and the current has to be present somewhere. All the charges that make up I total must be present in these two branches. So I total must be the sum of the two individual currents. And what we found in the series case was that the voltages across the resistances had to add up to the total voltage from the power pack. Here we have the currents in the two resistances have to add up to the total current from the power pack. So here we have a typical series resistance example. We've got a total voltage of 12 volts and the series resistances are a 4 ohm in series with an 8 ohm. So the series resistance formula says that R total is R1 plus R2, which is 4 plus 8, which gives us 12 ohms. That allows us now to calculate our total current over here. This IT can be done by V over R, where V is this and R is the total resistance. So IT is VT over RT, which is 12 volts over 12 ohms, which will give us 1 ampere. Now what if we were interested in the voltage here and the voltage here? Well, we can just use Ohm's law now with IT times this R to get that voltage and IT times this R to get that voltage. So if we call the first one V1, then V1 will be IT times R1, which is going to be 1 times 4, which means that V1 is 4 volts. And so we can perform the same trick on the second one and say that V2, the voltage across this one, is going to be IT times R2. And that's going to be 1 times 8 to give us 8 volts for V2. And as you can see, the total voltage at the power pack does equal the sum of the voltages across each component. So what we're basically finding out is that there is 4 volts here across this one and 8 volts here. And as you can see, they're in the same proportion as the sizes of the resistances themselves. So we will always find the big voltage across the biggest resistance when we have a sequence of them in series. So just summarizing that, when they're in series, we add them to get a total resistance. We can use that in conjunction with the voltage to get a total current. Once we have a total current, we can go back to the individual values and use that total current times the resistance to get the voltage across that one component. So this total current times this resistance gives us the voltage across that resistor. This total current times this resistance gives us the voltage across that resistor. And then we just confirm that these do add up to 12 like they should do. Now we have a typical parallel set. Now there's a few things we know about this before we even start. Firstly, there's 10 volts between here and here, which means there's 10 volts across this resistance and there's 10 volts across that resistance. Remember that components that are in parallel have the same voltage across them. That's part of the definition of something being in parallel, they have the same voltage between one end and the other. So it is possible to use this 10 volts and this 10 ohms to get current I1 just using Ohm's law. I1 will equal 10 volts over 10 ohms. So we can tell straight away that I1 is going to be an amp. I2 here is going to be 10 volts over 20 ohms. So it's going to be half an amp. And you can quite quickly go from this to working out what the current is. And interestingly, that does not necessarily require you to do a calculation on the total resistance, first of all, because you can find this current and then this current and realize that this current here is made up of these two, and therefore it must be the sum of them. So if we figure out this to be an amp and this to be half an amp, then this must be 1.5 amps. But we can also do a total resistance calculation using the other equation and confirm that the total current here is 1.5 amps by a completely different method, which is nice. So our parallel resistors equation says that 1 over R total is equal to 1 over R1 plus 1 over R2. So we write that out again with the numbers that we have been given in the question. When we do that, we find 1 over RT is the same as 1 over 10 plus 1 over 20. And we need to take a common denominator for that. We'll take 20ths, and a tenth is going to be 2 of those, and a 20th is going to be 1. So we get that 1 over RT is equal to 3 over 20. And this is where a lot of people would slip up, because this is an answer not for the resistance, but 1 over the resistance. So we have to invert both sides here to get RT on its own, and that means that RT will equal 20 over 3. So RT is going to be 6 2/3 of an ohm. At this stage, it should be possible for us to use this value and this total voltage and total resistance to work out total current. So IT is going to be VT over RT, which in our case is 10 volts divided by 6 2/3 of an ohm. And we do that, we get 1.5 as expected. So we get this answer of 1.5 amperes. As I say, we could have got that by another method, because we could have put this voltage across this resistance. So 10 volts over 10 ohms gives us 1 amp this way. 10 volts over 20 ohms gives us half an amp that way. 1 amp this way, half an amp that way gives us a total of 1.5 coming down there. So we can see how this circuit's going to pan out by different methods. Now, the actual exam questions that are set usually would have a little bit of series and parallel in it, as we can see in a moment. The question we're going to look at here is 3B from 2013 Unit 2 on the CCEA paper for GCSE. So they show you a circuit, and as you can see, they're giving us the voltage that's put across this circuit, and the circuit consists of a parallel section in series with a single resistor. And the way to solve this is to work out this parallel bit and then use the two resistors in series, just adding together what we get for this to the 3, and that'll give us a total resistance. So if we think of this section as being some R parallel, then that's the best way to deal with this problem. So I've separated the resistors from the rest of the circuit so that we can look at them in isolation. So if we think of this section as some resistor called R parallel, RP, then we can think of it in series with the 3 ohm resistor. So the circuit will simplify to a value RP in series with 3 ohms. And so if we know the value of RP, these two in series will just be added together to give a total resistance. So we need to find this RP value first. So for a parallel combination, 1 over RP will equal 1 over R1 plus 1 over R2. And R1 and R2 are this 8 ohm resistor and this 6 ohm resistor. So we need to find a common denominator in order to add these two fractions together. So taking 24 as the common denominator, then 1/8 will be 3 24ths and 1/6 will be 4 24ths. And so we get 7 24ths. Now, one of the most common slip-ups in calculating a parallel resistance is that they think this is the answer. But this is an answer for 1 over Rp. We need to flip both of these fractions to get Rp. And that's going to come to about 3.43 ohms. So now we know that this value over here is 3.43 ohms. And to find the total resistance of this combination, which will be the total resistance of this thing, we just need to add our 3.43 ohms for Rp to the 3 ohms that it's in series with. And so when we add those, we get 3.43 plus 3 gives us 6.43 ohms for our total resistance. Next part asks us to calculate the current flowing in this 3 ohm resistor. And that's really helpful because we now know that this thing has a total resistance of 6.43 ohms, and that combined with the known voltage will give us the current flowing from the power pack. Now, if we can find that total current, that'll be the same as the current in the 3 ohm resistor, because the total current must flow through the 3 ohm resistor. So if we can find the total current, we're automatically finding the current in the 3 ohm resistor. So all we have to do is Ohm's law for the total voltage and the total resistance to get the current we're after. So I total is going to just be V total over R total. And we have these numbers. So we get 12 over 6.43. And that gives us 1.87 amperes. In question 3D in 2014, again with the CCEA GCSE paper, asks a very similar question using a network of resistors that looks very like the one we've just looked at. You don't get a whole circuit this time, you just get an isolated part of a network of resistance with again a series and parallel combination. So we have some parallel thing in series with this 5 ohms, and so we just find the resistance of this and add it to that. And again, this circuit will just simplify to this, and once we know the value of Rp, we simply add these two. Very, very simple. So we start with our resistors in parallel equation, that 1 over Rp is going to be 1 over R2 plus 1 over R3. Taking a common denominator of 6, we get 3 plus 2 over 6. And that means that 1 over Rp is 5 over 6, which means that Rp will be 6 over 5. So 6 over 5 is like 1 1/5, which is 1.2 ohms. So our total will be R1 plus R2, which in this case is 5 plus Rp, which is 5 plus 1.2, and that gives us a total resistance of 6.2 ohms. So it's this process of simplifying a circuit and then working through the parts that need simplified. That's what you need to do in these resistor combinations.